Good morning, everyone. Today, we are going to have our discussion for module number 2, that is linear time invariant systems. Okay, so what we had done in the previous class was we discussed some of the properties related to signals or systems, where we had linearity property. Next, we had the stability aspect of it. Next, we had the causality nature of a signal. Next, we discussed about the time invariance property. Okay, so all these five properties were considered to be the most important properties that is related to the signals and systems. So let me start presenting my screen now. Yes. So here we are going to discuss about module 2, that is linear time invariant systems. Time invariant systems. Okay. So we are going to talk much about the two properties which are directly connected in a system, that is linearity property of a system and time invariant property of a system. So first one, that is linear property. As we all know that it is the principle of superposition where it generally follows, and we have the t operator that is operated on the input signal, and next we are going to have the time invariant nature of it. Okay, so time invariance or time invariant. Okay, so we say that the signal is said to be time invariant. So the first one, which is nothing but the linear property of the signal there. Okay, so along with that we are going to have few more concepts, that is with respect to the signal and system, and this module that is entirely with respect to the linear time invariant system there, right? So now when I talk about a linear time invariant system, generally we need to have the input signal, that is say x of n. All right, now it needs to be applied, as we generally talk here, that is an LTI system, and this one y of n is the output. So I'm referring to a discrete signal. I'm referring to a discrete signal here. Okay, so x of n is said to be the input signal and y of n is said to be an output signal. So y of n here would be x of n, where you need to convolute the signal, that is h of n. So h of n is said to be the impulse response of the system. Impulse response of the system. Impulse response of the system. So impulse response of the system is h of n. Okay, so now what I can generally talk here is with respect to the output y of n. So how I can write it in terms of the t operator, that is with respect to x of n. So when I write the signal x of n, that is the input signal, along with the t operator gives you the output signal. Okay, so I'm talking only about the linear time invariant system here. Okay, so one more concept that is related to the linear time invariant system is convolution. One more important topic that is related to linear time invariant system is convolution. So this symbol here, what it represents the convolution symbol. It represents the convolution symbol. Okay, so now a new word has popped up here, which is nothing but convolution. So hope you have heard in your previous semesters also. I'm not aware. This term convolution is said to be a mathematical operation that is being performed, mathematical operation. Okay, operation or mathematical equation. We have set of equations that are being performed. So I generally call this to be a mathematical operation that is performed, that is performed, that is performed on two signals. You can't apply convolution to one signal. You need to have two signals. Okay, two signals where it is linear, where it is said to be linear and time invariant. Okay, so time invariant, so you will be having the shift of time. Okay, generally you will be having a shift of time there. So here these signals, what I mean here, say f of n is said to be an output signal. You will be having two signal, g1 convoluted with g2, any two signals that are said to be generally convolution. So no need to put a circle here. So that refers to circular convolution. When I talk about circular convolution, that would be with respect to the digital signal process. Only we are talking about digital signal processing there in the next semester. Okay, so now once I talk about the word convolution, I just defined it as a mathematical operation that is being performed on two signals, that is said to be linear as well as time shifted, time invariant. Okay, so generally you will be having the time invariant property to be time shifted there. Generally you are shifting the time there. So here what we can generally talk is, why do we need convolution here? So why do we need convolution? Okay, so once I have any image, okay, so the areas what I'm talking here, it is with purely with respect to electronic systems here. So I have image processing to be carried out on certain images there. Okay, so I have two images that are being present there. So you will be having it observed as a two-dimensional axis there, right? So two-dimensional axis, that is how you can represent a image there. So once I can write a image, so I'll be having certain pixels over here. So that leads to the development of a image like this. Okay, so any image, it is nothing but the pixels are being interconnected, and there you can get the image there. So image is being processed. Okay, so once I'm talking about image processing, or you will be talking about speech processing, okay, language processing being done. Okay, so any such processing system, you will be having two signals being present there, right? So two signals being present. So in case if it satisfies the linear and the time invariant property, the linear and the time invariant property, so then you are going to call the system to be, so then it is generally convoluted. Okay, so it is generally convoluted. Okay, so you are going to call the signal to be convoluted in nature. So convolution operation can be performed easily. So that is convoluted. Okay, so the same thing, that is generally CNN. Okay, so convolution neural network. Okay, so I'm listing out one more area where you can generally call it as convolution neural network. Okay, so convolution neural network. Okay, where you are going to have the convolution operation being performed on the neural network in such a way that the convolution operation is being performed on it. So CNN. Okay, so convolution neural network is one thing. Okay, so now this is the reason why we will be going for convolution of signals, and irrespective of the magnitude. Okay, irrespective of the magnitude and phase, where we are going to have the shift in the time axis. Generally time is taken to be the predominant parameter there, and we are going to have the magnitude and phase which are being associated, and the frequency is one thing which remains unchanged. Okay, yeah. So next one, what we are going to have is a typical discrete time signal. Generally a typical discrete time signal, I can write it as the signal over here. Okay, so any signal 0, 2, 3, yeah. So any signal which is written like this, any values which are represented, so that is -2, -1, 0, 1, 2, 3, and so on. So this is x of n. Okay, so x of 0 is one thing that is there as some quantity, say 1. X of 1 is said to be 2. X of 2 is said x of minus 1, that is said to be 1, x of minus 2, that is said to be minus 2 there, right? So here are the quantities or generally the values at that instant of time. So this is the value of n, say equal to 0, and its magnitude that would be equal to 1 there, right? So this is n that is there, and you are going to represent the discrete time signal there. Represent the discrete time signal. Represent the discrete time signal. Okay, so that's how we are going to represent the discrete time signal as x of n. Now, so this x of n signal, as I already told you, impulse response of the system is to be associated with respect to x of n. Okay, so I need the weighted sum of the signal that is there at that particular time instant. Okay, what do I mean by that is, so I'll be having this signal like this in minus 3, minus 4, minus 5, and you can have such signals over here on the right hand side of the signal as well as the left hand side of the discrete time signal that is listed down there. So that is x of 0. Okay, I can write it down here. Now I need to have the sum of it. So it is x of minus 1, okay, plus x of minus 2, okay. So in the same way, you're going to list it down. So that is x of 1 plus x of 2, okay. So I'm going to list it down like this, okay, plus x of minus 2 plus x of minus 1 plus x of 0 plus x of 1 plus x of 2 plus, so in the same way it is being listed down there. So now I need to associate the impulse function in this x of 0, 1 and 2 then. So how do I associate it? Okay, so I can write it as x of minus 2. Okay, so I can associate with respect to the impulse function. So this is impulse function over here, right? So this is impulse function. How do I write it? So impulse function can be represented in a discrete domain as delta n. So now it is right shifted there. So delta of n minus 1. Okay, so n minus 1 once it is shifted towards the right. Okay, so that is a delayed signal and it is shifted towards the right. Okay, I mean sorry, shifted towards the left one, it is n plus 1 then, right? So I'm just giving you an example. Okay, so how I can write it? So delta of n plus 2 plus x of minus 1 delta of n plus 1 plus x of 0 delta of 0 plus x of 1 delta of n minus 1 plus x of 2 delta of n minus 2 plus it goes down there. So now this equation what I have written is associated with respect to the delta function there. Okay, so this is associated with respect to delta function. So this delta function over here having the values 1 and 0 when n is equal to 0 and n not equal to 0 there. So that is associated mathematically. That is associated mathematically. Okay, so that's what we had defined there in the fundamentals of signals and systems, and that is how we are going to define it in the future also. Yes, so there is no change there, and that's how it's going to be. So now I need to represent it over summation there, right? So how do I represent it over summation? I'll be using sigma. I'll be using another number called as k. K will be equal to minus infinity to plus infinity x of k delta of n minus k. Okay, so that is x of n. X of n. So I can represent it using summation. Represent it using summation. Yes. So I'm representing it using the summation sigma, that is x of n equals sigma x of k into delta of n minus k. Okay. So now the arbitrary response, that is y of n, that is t of x of n, that is present there, right? So that is the response of the system to an input x of n. Okay. Response of the system to input x of n. response of the system to an input x of n. So when I say x of n, it is generally the weighted inputs at each and every time there. So this x of n can be written over here. Okay, so I'll be applying a t operator there. So what do I'll be getting? That is sigma k equals minus infinity to plus infinity x of k delta of n minus k. Okay, so that is one thing that is being present there. So now x of k we can generally take it out because each and everyone will be having it. So now the t operator, what I told you, that is being applied. So sigma k is equal to minus infinity to plus infinity x of k. Okay, so the t operator I'll be applying on delta of n minus k. As we already know that y of n, as I already defined, it is x of n convoluted with h of n. Okay, so how do I get h of n? It is the impulse response. So once I say the impulse response, this acts as an output for the impulse input signal, or the signal which has been excited generally with a unit impulse function there, right? So unit impulse function, generally I'll be calling it as t of delta of n minus k. So this one, if you are having it right, so let me make a slight change here. So that is h of n minus k. Okay, so this is one thing that is being given there, right? So you are going to have y of n that is equal to sigma k equals minus infinity to plus infinity x of k. So this term here, what I am representing over dotted circle, so that term entirely is with respect to h of n minus k. Okay, so which is nothing but the impulse response of the system. That is the impulse response. Okay, impulse response of a system. Okay, so impulse response of a system. So h of n minus k, that would be equal to t of delta n minus k. Okay, so this is the impulse response of the system that is being present there, right? So now the system under investigation is generally the linear time invariant system. So where h of n is the impulse response of the system. So h of n is the impulse response of the system for your notice. Okay, so impulse response of the system, impulse response of the system. Fine. So now I have y of n that is equal to sigma k equals minus infinity to plus infinity x of k times h of n minus k there, right? So y of n that would be equal to sigma k equals minus infinity to plus infinity x of k h of n minus k. So as I already defined earlier itself, so this term y of n is called as x of n convoluted with h of n. So that can be written as sigma k equals minus infinity to plus infinity x of k h of n minus k. Okay, so that is the symbol. I already repeated. So symbol convolution, the star that represents the convolution operation. Star stands for convolution operation. Stands for convolution operation. Okay, so star stands for convolution operation there. So that is nothing but the response of the system, that is h of n. Fine. So next one, what we have there is some properties which are related to convolution sum. Okay, so that is the equation that holds good for a discrete system. Okay, so you have y of n. Let me write it down here. That is defined as x of n convoluted with h of n. Okay, so y of n that would be equal to x of n convoluted with h of n. So properties of convolution sum. Properties of convolution sum. Okay, so that is one thing that has been associated there. So the first property here, that is a basic property of any system or any mathematical equation that is there, that is commutative property. So what is commutative property then? So x of n convoluted with h of n, is it equal to h of n convoluted with x of n? So can I interchange it? So with respect to the impulse response being written second, can I just change it to the first, and whether I can verify whether the commutative property holds good. So verify for the convolution sum whether the commutative property holds good. Okay, so let's go step by step as y of n, that is the output of an LTI system. I repeat, y of n is called as the output of the LTI system. So x of n convoluted with h of n. So how I can write it? Sigma k is equal to minus infinity to plus infinity. So x of k, first one, that is x of k, h of n minus k then, right? So this is how I can write it. So let me mark it as equation 1. So now let me take any variable, say m, so that is equal to n minus k. Say any variable m can be any variable, can be any variable, okay, where it is equal to n minus k. So m will be equal to n minus k. Okay, so I can write it as n minus k equals m, or n minus m, that would be equal to k. Fine. So now I can write down this to be sigma, that would be equal to, that is any variable I can generally choose it. Okay, so I can write down to be k. What I can replace k as? So I can replace k as x of n minus sorry, 1 minute, x of n minus m, x of n minus m. Okay, so next you'll be having n minus k, that is h of m. Okay, so what do I need to replace the summation with? I need to replace the summation with m is equal to, that is minus infinity to plus infinity as k there. Okay, so you will be having n as the term there, right? So m will be equal to the value, that is you'll be having n minus m, so you'll be having it to change from plus infinity to minus infinity. N is a variable that is already being associated with respect to time. Okay, so k can be replaced with n minus m equals plus infinity, or any variable again you'll be having it replaced by plus infinity to minus infinity. So now it's a summation. We can interchange the summation because it is a discrete time in nature. So m can be replaced with minus infinity. I'll write it in the next page. So that is sigma m equals minus infinity to plus infinity x of n minus m, that is h of m. Okay, so where m is any dummy variable that can be replaced again, because this term, what I can write here. Okay, so what I can write here for x of n minus m into h of m, I can write it as the convolution nature, which is already being there, right? So what I can write here is, I can write x of n convoluted with h of n to be equal to sigma m equals minus infinity to plus infinity x of n minus m h of m. Okay, so this term here, where m is any dummy variable, we can replace it with k there, right? So sigma k equals minus infinity to plus infinity. Okay, so where you will be having x of k into x of n minus k, h of k into x of n minus k. So that would be again h of n convoluted with x of n. Okay, so this is x of n convoluted h of n. You will be having it replaced where m is a dummy variable. Okay, m is a variable or a dummy variable, we are going to call it. So now this term here, where I am going to represent again h of n convoluted with x of n, how I can write it? So sigma k equals minus infinity to plus infinity h of k x of n minus k. Okay, so that is what you can write it as, x of n convoluted with h of n again. So this is one thing which will be constant there. So that's how we can write it as x of n convoluted with h of n, that would be equal to h of n convoluted with x of n. So commutative property holds good. Commutative property holds good. Commutative property holds good. Okay, so this is how we can practice again. So you just have to replace the variable, and then you can just have the variable which you have been replaced. It can be replaced by k again. Okay, so you can call any such variables for your understanding, and you can verify the commutative property to be clear then. Okay, so next you have the associative property. Associative property. Okay, so now x of n, so you will be having x of n convoluted with h1 of n. Okay, so under the bracket, so convoluted with h2 of n. So that is x of n again convoluted with the convolution operation being performed on h1 of n and h2 of n. So first convolution you are going to perform on the input signal and the first impulse response, say h1 of n. So then you are going to have that result being convoluted with h2 of n. Next one, what you are going to have is x of n convoluted with the result of two signals, that is h1 of n convoluted with h2 of n. Okay, so we have to verify whether it is the associative property holds good or not. So x of n convoluted with h1 of n, so then that whole result is to be convoluted with h2 of n. So is it equal to x of n convoluted with h1 of n convoluted with h2 of n? So now let us start with the proof now. I can call it to be function 1 and function 2 for your understanding. So this entire term, I can call that to be the first function f1 of n. So this one to be equal to f2 of n. So for your understanding, say f1 of n to be equal to x of n convoluted with h1 of n, and f2 of n to be convoluted with h1 of n convoluted with h2 of n. Fine. So f1 and f2 are to be listed out here. Say x of n and h1 of n, say that is for f1 of n. So f2 of n, that would be equal to h1 of n convoluted with h2 of n. Fine. So let me start with the first function, that is f1 of n. Okay, so I need this output, I need to convolute it with h2 of n. So whether I need to verify this h1 of n will be the same, that is the associative property holds good or not, I need to check it out. Okay, so f1 of n again, that is x of n convoluted with h1 of n. So how do I write it? So I can write f1 of n to be equal to sigma k equals minus infinity to plus infinity x of k h1 of n minus k, right? So next what you are going to have, you are going to have this function, say f1 of n convoluted with h2 of n, right? So that's how we are going to verify this function here, that is f1 of n, okay, convoluted with h2 of n. So that would be equal to, so you are going to convolute the signals over here. Okay, so how I can write it with another variable being replaced, that is sigma m, any other variable, say minus infinity to plus infinity f1 of m. So whatever the k variable that is there here, so you are going to replace to this function, and at the same time, so f1 is a signal. Okay, so then you are going to replace with h2, sorry, f1, yeah, h2 of n minus m. Okay, so that's how you are going to get there. Now this f1 of m can be replaced with this summation here. Okay, so this summation here, that you can write it, so where you are going to have f1 of m being written there, right? So it might be any such signal there, so you are going to have m minus k. Okay, so if you have f1 of n, it will be n minus k. F1 of m, it will be m minus k. Okay, so that's how you are going to write it. So what holds good here? So I can write it to be sigma m equals minus infinity to plus infinity. Again, this function over here, that is sigma, fine. So that is k equals minus infinity to plus infinity x of k h1 of m minus k, right? So next you are going to have h2 of n minus m. Okay, so this summation is being replaced here as f1 of m, which is nothing but this value over here. Now I'm going to have this function to be with respect to h2 of n minus m there, right? So a bit of understanding needs to be present here. Okay, so again, let me take another variable, say tau, that would be equal to m minus k. Okay, that would be equal to m minus k. So interchanging the order of the summation here. So what I can generally use the summation as, so sigma k equals minus infinity to plus infinity, that is there, and again sigma, that is tau. Okay, so tau might be any other variable, that is x of k, that needs to be written here. So I'll take down this outside entirely. So what I'm left out is, so this tau, that would be equal to minus infinity to plus infinity h1 of tau, h2 of n minus k minus tau, right? So that one under the bracket. So now in the similar fashion, you are going to have f2 of n being written there. So f2 of n, okay, sigma, say any other value, say r minus infinity to plus infinity h1 of, yeah, just a moment, h1 of, yeah, so it might be any value, say let me use it as tau itself for your understanding. Tau, this is tau. Okay, so h1 of tau, h2 of n minus tau then, right? Next, f2 of n minus k, that is again sigma tau to be equal to minus infinity to plus infinity h1 of tau, h2 of n minus k minus tau. Okay, so where you will be having the function, that is sigma k equals minus infinity to plus infinity x of k f2 of n minus k, that is equal to x of n convoluted with f2 of n. Okay, so that is x of n convoluted with, what is f2 of n? So that is h1 of n convoluted with h2 of n. So that is the value that holds good, that is associative law holds good. Associative law holds good. Okay, so you have to practice it again and again to get a good understanding of it. So associative law holds good for the function then, right? So next, a quite simple one, that is distributive law. Distributive law. So where you will be having a signal x of n that is convoluted with the sum of the signals, that is h1 of n, okay, plus h2 of n, that would be equal to x of n convoluted with h1 of n plus x of n convoluted with h2 of n, right? So now what is the convolution of these two things we have to verify? Okay, so I have the left hand side, let me take the left hand side here. So what I can write it as, sigma k equals minus infinity to plus infinity x of k, and I need to shift the impulse response n minus k plus h2 of n minus k. Okay, so now let me multiply it inside. So that is sigma k equals minus infinity to plus infinity x of k h1 of n minus k plus sigma k equals minus infinity to plus infinity x of k, h2 of n minus k. Okay, so this is the two things that is there. So what I can write it as, so this one which is x1, oh sorry, this is x of n. Okay, so x of n into h1 of n plus x of n into h2 of n. So that is x of n, okay, into h1 of n plus x of n times h2 of n. Okay, yeah, that is nothing but the convolution here. I just missed out here. So this is nothing but the convolution. Don't miss convolution operator, that is star mark. Okay, so next I have two sequences, that is identity sequence. Identity sequence. Okay, identity sequence, which is x of n convoluted with delta of n, that is equal to delta of n. What we proved right now was the property of commutative property holds good, that is delta of n convoluted with x of n. So that would be equal to x of n alone. So identity sequence, when any signal, any given signal, x of n is convoluted with delta of n. With delta of n, you are going to have x of n itself. You are going to have x of n itself. So x of n convoluted with delta of n, that would be equal to delta of n convoluted with x of n, that would be equal to x of n again. Okay, so now the next one, what is requested is the convolution of a delayed input signal. So when the impulse sequence is delayed, when impulse sequence is delayed, when the impulse sequence is delayed, what it is x of n convoluted with delta of n minus k, that would be equal to x of n minus k. Okay, so that is the signal is shifted, that is the delay of a input signal can be written directly. So these are important identities which will be generally asked in your competitive exams. Okay, so once you are having two delayed impulse signals, what would be the case? So convolution of two delayed unit impulse response, unit impulse response, unit impulse response. So what you can write it as, so delta of n minus m and delta of n minus k. Okay, so delta of n minus k convoluted with delta of n minus m. So you'll be having delta of n minus m plus k. So whatever the value, what you can write, for example, so delta of n minus 2 convoluted with delta of n minus 3. Okay, so that would be delta of n minus 2 plus 3. Okay, that is 5. Delta of n minus 5. So you can write it like this. So straight away you can write it, and the value, that is delta of n minus 5. Okay, that is 1 and 0. N minus 5 would be equal to 0, that is n equals 5, and n minus 5 and not equal to 0. So any other values other than 5, it will be 0 there, and it will be 1 only at n equals 5. Okay, so that is how you can write down different properties that are associated with respect to a linear time invariant system when a convolution sum is being applied. Okay, so we will stop here. Okay, so we will stop here. Meanwhile, in the next class, we are going to come up with a numerical problem, and we are going to discuss few more properties that are associated with respect to the convolution sum there. Okay, we will stop here right now.